Okay, so I want to talk about some work that I've been doing. It's actually work that goes back a little ways away to 2018 already with Chris Lau, who's a postdoc in Taiwan. He's a postdoc in Taiwan. Chende Ma, who's technically a postdoc with us, but he's stuck in China for obvious reasons, and Masaki Tezuka, who's faculty at Kyoto University. This immediate work is based on a paper that we put out on the archive earlier this month, and the archive number is listed there. So this is going to be roughly a Blackboard talk. So I'm going to write down things on my iPad, and hopefully it's going to show up on everybody's screens. So let me know if there's something that's unclear, and I'll be happy to go over it again. So by way of an outline, I want to start by giving a motivation for what we're going to be working on. And then I want to introduce the idea of the spectral form factor, which is a useful diagnostic tool for what we want to do, which is essentially think about quantum chaos. I'll follow this up by talking a little bit about the SYK model, and I want to basically focus on the whole family of models. They're what we would call the SYK-Q models, Q being the order of interactions amongst the fermions. And this is an extension of stuff that we did in 2018, which was looking at one particular member of this family where Q equals 2. So this is fermion-fermion interactions in this particular class of models. What's new in this work that we did was that we coupled in the model with sources of a particular form. And I'll show how we were able to get some exact results for the particular case of Q equals n, the number of fermions equals 2. And this more or less serves as a, let's say, a prototype for more general results. But because it's exact, we have a good handle on the solutions. But once you go to higher number of fermions, then you have to do things numerically, and we do that. So for n greater than 2 fermions. So I'll go over some of the numerical results we got, and then I'll talk about some lessons that we can extract from this. Okay. So by way of motivation, then, let me start off then by making a very simple is that if you think about the world from a Wilsonian effective field theory point of view, then it's actually remarkable how much of the world we actually understand. In particular, if I organize things by, let's say, speed versus size. So let's put on this axis down here. we'll put down speed. And up here, we'll put down size. Then our description of things that are slow, and slow here will mean slow relative to the speed of light, and small, small meaning, let's say, atomic scales, is one described by quantum mechanics. And then staying at those subatomic scales but increasing speed takes us to quantum field theory. On the other hand, for speeds that are large relative to the speed of light, but large things, so cosmological scales, let's say, or galactic scales, astrophysical scales, this is well described by general relativity. And then on this top right-hand corner of large now, meaning up to, let's say, planetary scales, but slow relative to the speed of light, we have Newtonian classical mechanics. So that's great. That gives us this that gives us this Wilsonian description of the world around us. But because it's an effective field theory description, it's not clear where one description ends and where one description begins. So essentially the story is that if I want to understand the transition from quantum mechanics to classical mechanics, then I have to integrate out all degrees of freedom above a certain scale. And the process is certainly clear enough to implement. And the same is true in going from, let's say, quantum mechanics to quantum field theory, or quantum field theory to quantum mechanics. There's a limiting process where I expand things in let's say, 1 over the speed of light, and then organize an expansion in this way. So that's very nice. It gives us a nice description of the universe around us. However, what's less clear is where the transition between these different descriptions lie. So, for example, the transition between quantum field theory and GR, or let's say classical mechanics and GR. We know how to organize the degrees of freedom in a way that allows us to discard some, but it's not clear where whether there's any sharp transition between the two, or in some cases, how to effect the transition. So here's a case where effecting the transition is actually quite important. And that's the transition between classical and quantum mechanics. And this is a transition that's particularly important. So this transition is important in trying to understand, for example, quantum computing or systems biology. So if we want to understand processes like this, then we need to understand how this transition between classical and quantum mechanics works. This is obviously a very hard problem. It's one that we've been grappling with as a community since the inception of quantum mechanics back in the early part of the 20th century. And it's not for lack of trying. So what we do typically then to understand things like this transition is we study toy models. So to understand this, we then need good toy models. The emphasis here being on good. Okay. So then it's worth asking, what constitutes a good model, a good toy model? Since we've already decided it's a toy model, we don't really need to focus on reality that much. But what we would like to have is something that is conceptually simple. It should preferably be solvable, or at least tractable. And it shouldn't be too specific in the sense that it should exhibit sufficiently generic features. That will allow us to draw some general lessons and then go from there. So one such feature that seems to be more and more, let's say, important. No, that's not the word I want to use. One such feature that's becoming, that we're realizing is more and more important in such considerations is chaos. And the reason for this is because it seems, the more we think about it, that nature is generically chaotic, and anything else that we find, like integrable systems that I can completely solve, these are very, very specific systems that are highly constrained and that allow us to probe them in exquisite detail because they're so highly constrained. But generically, nature appears to be more chaotic than some, let's say, integrable. So what is chaos then? Well, classically, chaos is the hypersensitivity of a system to perturbations in its initial conditions. And a classical example here is that of the Sinai billiard system. So here you have a box, and in the center of the box, you put a circle to provide some kind of stadium in which you throw some billiards around. And the point here is, if I start off some billiard ball rolling in this box, and I let it evolve, then it bounces with well-defined stop that. So it bounces in a well-defined way. And goes about its way. If I start off another billiard, let's say very, very close to this one, then in the Sinai billiard system, After a few bounces, this green trajectory finds itself very, very far. Let's count 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Yeah. This green billiard finds itself exponentially far away from the red one in phase space. So the point here is that there is that small changes in initial conditions result in exponentially large deviations at late times. Okay. Sorry, guys, give me 1 second. Okay. Sorry, I just go back to my notes. Right. So that's classical chaos. The question is, how do we characterize the quantum problem? And the reason why this is an interesting question, well, this is a difficult question, is because by Heisenberg uncertainty principle, we lose the concept of well-defined paths in phase space. The phase space, by definition, in going from a classical to quantum system, becomes noisy, and it's an inherent quantum noise that's characterized by the uncertainty principle. So if we don't have the idea of well-defined paths in phase space, then we can't talk about exponentially divergent paths in phase space. So then we have to ask about how we would possibly characterize chaos in quantum systems. And fortunately for us, this was work that was done by pioneers in the field of quantum chaos back in the 1970s, and pioneered essentially by Michael Berry. Understood what one should do is focus on spectral analysis of the Hamiltonian of the system. So that's great. We have a Hamiltonian operator that characterizes the quantum system. let me just check something quickly. Can you guys all unmute yourselves?
Yep.
Okay, good.
Yeah.
Yeah, that's fine. I just want to, it's difficult to run the meeting and give the talk at the same time. So if you can unmute yourselves and you have a question, then please feel free to just chip in at any point, okay? So the problem with this idea of spectral analysis is that when we talk about spectral analysis, I give you some Hamiltonian operator, which is a large matrix, essentially, and to extract the energy spectrum of the system, what you need to do is diagonalize the matrix. And the bigger the matrix becomes, the harder it is to diagonalize the matrix. So the problem with this idea is that diagonalization of large matrices is hard. So then it was discovered by people studying essentially very excited nuclear states, specifically Wigner and Wigner and Dyson, that a better thing to do would be, instead of trying to exactly brute force diagonalize the Hamiltonian, you applied statistics to the energy levels of these highly excited nuclei. So this led to the idea of spectral statistics. Which is much easier to use to analyze many of these systems. So then people studied these quantum chaotic systems some more, and came to the following conjecture. The conjecture is that any quantum chaotic system with a classical limit eventually will start to behave like a random matrix theory. So this is a theory of matrices with random entries in them. So the conjecture is that a quantum chaotic system with a well-defined classical limit leads to random matrix statistics. That is the statistics of random matrices. And this in itself leads to eventually a novel new diagnostic for quantum chaos, which we will call the spectral form factor. I'm going to elaborate on the spectral form factor because it plays a central role on what we're going to say. Okay. So I should tell you then what the spectral form factor is. Very simply, it is the Fourier transform, like most form factors, the Fourier transform of the spectrum of the Hamiltonian with respect to the energy level difference. Fourier transform of the spectrum with respect to the level difference. And it has some rather interesting properties which lead us to use it as a diagnostic for quantum chaos. One is that it can possibly disambiguate between actual quantum chaos in the sense of what we expect from classical treatment, namely hypersensitivity to some perturbations. Of course, we can define perturbations in a quantum system as well at the operator level. So disambiguate between quantum chaos and simply random systems, so randomness. So randomness that is not chaotic. And the way it does this is because it exhibits a very particular form when computed for a quantum chaotic system. So it displays a characteristic dip ramp plateau behavior in a quantum chaotic system. Okay. And I'll show you where this comes from, where this type of behavior comes from, and how we ought to think about it, and how it helps to disambiguate between integrability, chaos, not chaotic behavior, and randomness in a toy model to follow. So toward this end, let's then consider a toy model. The toy model that I want to focus on is the so-called SYK model. And the SYK model is named after its discoverers, Xavier Sachdev, his graduate student at the time, Yi, and then many years later, Alexei Kitaev, who used the model to do something completely different from what Sachdev and Yi had been studying. So Sachdev and Yi came up with a model which was called the SY model, I guess, back in the 1990s, when they were trying to understand some properties of what are called glossy systems, so spin glasses. And then Alexei Kitaev tried to simplify this model and found that actually he could use it to describe black holes in quantum gravity. So I don't want to talk about the Sachdev-Yi model at this point, but I want to focus a little bit on the SYK model. I've spoken about the SYK model in this forum many times, so I'm going to give a quick review of the model for those of you who don't find it as compelling as I do. So didn't pay much attention when I was talking about it the last time.
Prof, sorry, I just have a question about the spectral form factor.
Yeah.
So initially, when you introduced the idea, you said it like historically came from trying to avoid having to diagonalize large matrices. But on the previous page, you seem to be saying that it's the Fourier transform of certain aspects of the spectrum. So do you not then need to have already found the spectrum in order to...
No, so I don't need the spectrum. All I need to know is the spectral statistics.
Okay.
So and in fact, I don't need to know. In fact, I don't need to know that very much at all. I'll show you that the spectral form factor is actually an analytic continuation of the partition function of the system. So if I know the Hamiltonian, I can analytically continue the partition function, and that will allow me to read off what the spectral form factor is. So that's a good question. So I don't need to brute force know the spectrum. Right? In the same way that I don't need to know the spectrum in order to do spectral statistics. I just need to know roughly what the system how the system behaves at late times.
Cool.
Okay. So the SYK model is a 0 + 1 dimensional quantum mechanics of n Majorana fermions with all-to-all random interactions. So that's a mouthful, so let me write it down. This is a 0 + 1 dimensional quantum mechanics of n, and in general we will take n to be large, Majorana fermions, so these are real fermions. Call them psi A, and these have all-to-all random Q Fermi interactions. And we're going to be interested in particular values of Q, as were SY and K. So the standard SYK model is a 4 Fermi interacting model in 0 + 1 dimensions. And for a long time, even after Kitaev was studying this, it was thought that the Q = 2 model, the 2 Fermi interacting model, so this is, one wouldn't really call this interactions, one would call this just a massive Q Fermi interacting model. Sorry, a massive Q Fermi model was trivial. And it was trivial essentially because you're trying to extract chaotic properties of this model. And even with randomness, it turns out that this Q = 2 SYK model, which we will call SYK2, the SYK2 model is integrable. So it's integrable in the standard sense of the word integrable. I can completely solve it. I can completely solve it because it's a highly constrained model, and by completely solve it in this case, because it's a quantum field theory, because it's a quantum mechanics problem, it means I can write down all point correlation functions in the quantum theory that I want. So the action for the SYK model, and let's say the SYK4 model, just for concreteness sake, is given by an integral over time of the sum over a going from 1 to n of psi a dot plus sum over A, B, C, D, say, also going to n of 1 over 4 factorial times J, A, B, C, D. Psi A, psi B, psi C, psi D. So this is what I will mean by 4 Fermi. So there are 4 factors of psi here. So this is the 4 Fermi interaction that corresponds to this 4. And this guy here is a random coupling drawn from some distribution. And in SYK, the distribution is usually taken to have 0 mean, and a Gaussian distribution with 0 mean and variance equal to 3 factorial j squared over n cubed. Okay, so that's the SYK model. So this is the thing that people have been studying rather frenetically for the past 5-6 years or so. It has a number of very, very interesting properties that gives it its appeal to not only condensed matter physicists, but also high energy theorists these days. Among these properties are the following. The first is that it is solvable. At 0 temperatures and large n. So in the limit where the number of fermions goes to infinity and the temperature of the system goes to 0, you can solve the system. And you can solve the system by writing down all correlation functions that you can think of between the psi's. It has an emergent conformal symmetry at low energies and again at large n. And it is maximally chaotic. In the following sense. So a chaotic system can be characterized by something called the Lyapunov exponent. So I said earlier that in a classically chaotic system, the trajectories in phase space are exponentially divergent. The coefficient of time in that exponential divergence, so if it goes like e to the something t, that something is called the Lyapunov exponent. So in a quantum mechanical system, you can define a similar quantum Lyapunov exponent, and this quantum Lyapunov satisfies something called the Modesena-Shanker-Stanford bound. And the MSS bound is that the quantum Lyapunov exponent must be less than 2 pi times the temperature of the system. Okay, so this is the temperature, this is the Lyapunov exponent, and lambda must be less than or equal to 2 pi times t. Well, the SYK model saturates this bound in the sense that if I go and calculate the Lyapunov exponent for the SYK model, then lambda turns out to be exactly 2 pi times the temperature of the system. Okay, and as I said, the conventional SYK model is what we would call in our notation that we've been talking about the SYK4 model. So I can have a Q-body interaction between the fermions. If I choose Q equal 4, this is what would normally be called the SYK model. We want to focus instead on a slightly simpler model with slightly different properties, but that will nevertheless prove quite interesting. That I'm going to call the SYQ equals 2 model. Okay, I'm going to try and make clear why this is an interesting model just now. So are there any questions? Okay, so if not, let me proceed then, having written down already the action for the SYK model in general. Let's proceed by writing down the partition function for the SYK2 model. So this we'll call SYK2, and it looks as follows. So let's leave some space there. This is to indicate that I'm integrating out over all the fermions. E to the minus the integral over tau. And the reason I'm using tau is because I'm going to Euclideanize this for now, and I'm going to use, sorry, I'm not going to use, I'm going to use t for the analytic continuation variable. So sum over j from 1 to n of psi j dot minus I times the sum over I1 and I2, also going to n, of curly j, I1, I2, psi I1, psi I2. And then this is an exponential, this is a weighted exponential, so it's weighted by measure, sum over I1, I2, again curly j, I1, I2 squared times n over 2j squared. So this is the n over 2j squared factor that comes in from the fact that I'm using a Gaussian, I'm sampling these mass matrix, if you want, from some Gaussian distribution. With zero mean and variance j squared over n. So this j squared over n factor is where this comes from. Okay, and then because I'm writing on the partition function, I have to then integrate over all of the j's. Okay. Right. So this is the partition function for the SYK2 model. This is what we studied in our previous paper. And while it's interesting, it's not really what we want to do here. So what we wanted to do in this paper was try and understand why this SYK2 model, which you would naively think is quite a trivial model because it's integrable. Yet what we were seeing were some interesting features of the spectral form factor that seemed to indicate that it was richer than we were giving it credit for being. So one way to try and understand what was going on was to ask what would happen if, instead of just considering the disorder being generated by essentially just Gaussian random variables, we correlated the noise. So we added some pieces to the noise that allowed us to couple in some source terms in the following way. So instead of considering just the JI1I2, we coupled in a source term. Well, whenever you couple in a source term in a partition function, that generalizes the partition function to what you would call in quantum field theory a generating function. So instead of considering the partition function above, let's consider the following generating function. And I'm going to denote this by GSYK2. And again, I'm going to be integrating this guy over all the coupling, over all of the J's and the fermions, e to the minus the integral d tau of let's do this, a half sum over j of psi j dot minus I times the sum over I1, and to avoid double counting and a factor of 2, we can just sum over I1 less than I2. Again, curly j I1, I2, psi I1, psi I2. So far, nothing different from what we just had. But now I add to this a minus, let's say I to the p, sum over all of these indices, sum k I1 through to k I2p, psi I1 through psi I2p. Same Majorana spinors. That's correct. And then in addition, I have an e to the minus sum over I1 less than I2 again of j I1 I2 squared times n over 2. And the reason I have an n over 2 here is because I'm going to, because it's not really going to play any role in what follows, I'm going to set j equal to 1 in what follows. The k here, this guy here, is the strength of the source term.
Sorry to interrupt. Rue disconnected and can't get back on.
Ah, okay, let me just let him in.
Cool, thanks.
There we go. Rue, are you on? Rue, are you in? Rue, are you in?
Yes, yeah, thanks.
Okay.
Thanks, Jeff.
Cool. Okay, cool. So that's the strength of the source term. All right. So I want to make one more point, which is that it will be, well, okay. Because of the fact that the K I1 to I2P multiplies a bunch of Majorana fermions, and the Majoranas have an anti-symmetry property that they inherit from the algebra that they must satisfy. The K has to be completely anti-symmetric in all of its indices. So then, given that the K is anti-symmetric in all of its indices, it will be useful for us to write K let's say I1 through I2P as alpha 2P, some constant parameter, multiplying epsilon I1 through I2P. Okay, so all of the anti-symmetry property of the coupling constants is contained in the anti-symmetric tensor, and we will use the freedom that we have to tune the parameter the freedom that we have in tuning the strength of the coupling. We will use as a dial this alpha 2P. The key feature here is that while this guy, the mass matrix, the coupling, is a random variable that if we take, let's say, a quenched random variable, we have to draw every time we do an experiment in this theory. We have to pick some coupling constant from this Gaussian distribution. The K's are fixed. They're just a constant. Okay? So that's the difference between these two types of terms. Okay. So now let's write down the spectral form factor then for this theory. In fact, we can go ahead and write down. Okay, I'm going to write down the spectral form factor, and then I'm going to show you that it very straightforwardly generalizes to the theory with sources. So let's start off by writing the spectral form factor. And I know that I said earlier that the spectral form factor is the Fourier transform of the spectrum with regards to the level difference. But you can show that given that definition, that the spectral form factor G of T and beta, where beta here is the inverse temperature, so beta is 1 over T, capital T, the temperature. This guy is written in terms of the analytically continued partition function. So I'm going to just write down things and then I'll unpack it as it comes. So there's two different types of spectral form factor. One I'm going to call annealed, and the A is for annealed, and annealed means the following. To calculate this guy, what I do is I calculate the partition function, or write down the partition function, which is usually Z is a function of beta. I then analytically continue beta to beta minus I times some parameter t. That's the t here. And that gives me a function of beta and t. And then depending on the theory that I'm using, if I'm using the SYK model, for example, then I write down the partition function for SYK. But for our generalized SYK model, I can just write the generating function, SYK2. Okay, so the same partition function, the same generating function we wrote down in the last slide, I write down here. I then take mod squared of this guy, and then I take the average of the mod squared of z, and the average I compute by running the experiment many, many times. And remember, I said that each time I run the experiment, I have to take a different sample for the random couplings. So every time I run the experiment, the coupling constants are different, and I take the average over those coupling constants, and then I divide this guy by the average of mod z g s y k 2 of beta, but now at t equals 0. And again, I compute the average over the realizations of the system. All right, so this is what's called the annealed spectral form factor. There's another spectral form factor that I can calculate. That's called the quenched spectral form factor. And here I calculate ZGSYK2 beta t over ZGSYK2 beta t equals 0. Divide the two, compute mod squared, and then compute one average over the realizations. And this is called a quenched spectral form factor. So again, this is the annealed spectral form factor, and this is the quenched form factor. So here, Z of beta and t is defined to be the trace over e to the minus beta minus I t. So I analytically continue the temperature, inverse temperature. Beta is 1 over t. And for some operator q or some function q, this average is computed over different realizations of the system. Okay, is everybody happy with that? I'm going to take silence as yes. So before showing you all of the numerical stuff, so there's a lot of pictures coming up, but before showing you the numerical stuff, this system is actually really nice because it's so simple that we can actually compute the spectral form factor exactly and use it to read off, because essentially when you have only quadratic variables, everybody, you know, whenever you see quadratic variables, as you would in the case of q equals 2, you should always think of Gaussians, and everybody can integrate Gaussian integrals, and this is why the system is so straightforward. So the system is straightforward enough that we'll be able to compute the spectral form factor in a very particular case, and this will tell us, it will teach us essentially what we need to know. Well, it'll teach us where some of the features of the spectral form factor come from in more complicated systems. So let's focus then on the case of, and again, we're talking about SYK2, so we've already set Q equal to 2, but we're going to focus on the very special case of 2 fermions. So we'll set n equals to 2 as well. So here, the Hamiltonian for the system, let's call it the generalized SYK2, is I times J12 plus alpha 2 epsilon 1 2 psi 1 psi 2. Okay, so that's a pretty straightforward looking system. And in fact, we can make it even simpler by doing what's called a Jordan-Wigner transformation. And the Jordan-Wigner transformation allows us to write this Hamiltonian, which is currently written in terms of fermions, in terms of spin variables. So I'll write psi 1 as sigma x over square root of 2, psi 2 as sigma y over the square root of 2. With sigma x and sigma y being Pauli spin matrices. And in terms of which our Hamiltonian, I'm going to leave the subscript because it's clear what I'm working with, just becomes minus a half this J12 plus alpha 2 times sigma z, again, sigma z being a Pauli spin matrix. Well, in this form, because I know the properties of the Pauli spin matrices quite well, I can easily read off the eigenvalues of this Hamiltonian. And they are nothing but E, let's call them plus minus, and E plus minus are plus minus a half J12 plus this alpha 2 parameter. The corresponding eigenvectors are 0, which is the vector 1 0, and one, which I'm going to use to denote that vector. And that's it. We have diagonalized the matrix. We've read off the eigenvalues, and we know what the eigenvectors are. And so we can use this then to compute mod of z g s y k 2 of beta t squared averaged over the realizations. And the average over the realizations in this case means integrating over the J12s from all values that it can take from -infinity to infinity. So this is how I calculate the average. D J12 integrate over the couplings. E to the minus beta J12 plus alpha 2 plus e to the plus beta J12 plus alpha 2 plus the cross term, which gives us 2 cos of J12 plus alpha 2 times t, all weighted by this Gaussian factor J12 e to the minus J12 squared. And this you can calculate by completing the square and doing the Gaussian integral. Comes out to minus e to the minus t squared over 4 times the square root of pi times things that come from the completing of the square, e to the quarter beta squared minus 4 alpha 2 beta squared plus not beta squared, beta plus t squared times 1 plus e to the 2 alpha 2 beta plus 2 cos alpha 2 times t. All right. The denominator we get by just setting t equal to 0, and we can divide the two, and this gives us an expression for the annealed spectral form factor, an exact expression for the annealed spectral form factor as e to the minus t squared over 4, e to the quarter beta squared minus 4 alpha 2 beta plus t squared times, what did I have above? E to the 2 alpha 2 beta plus 2 cos alpha 2 times t. Check if I've got all the factors, yes. And all of this divided by the same expression except with t equal to 0. So that's just e to the quarter of beta squared minus 4 alpha 2 beta times 1 plus e to the 2 alpha 2 beta plus 2. That's fantastic. So this is an example where, again, it's simple enough that we were able to now just write down the exact expression for the spectral form factor.
Jeff, can I just ask
Yeah.
So you've written down the spectral form factor there, but you originally said that the properties of chaos and whatever only show up when you're thinking about large n, but you've explicitly set n equal to 2. So what are you really learning about the chaotic properties of the system or anything like that at such a small value of n?
Very good. Very good. I'm not learning anything about the chaotic properties of the system yet. Essentially, the statement is the following. I want to see where the various properties of the spectral form factor, like this dip, ramp, plateau, come from. And it's very hard to see where they come from when all you have at your disposal is numerical calculation of the spectrum, or at least of the spectral statistics. And in order to see anything, you have to average over a large number of realizations of the system. Okay. So what I'm hoping to learn from this is that in this simple form, where am I seeing the emergence of, let's say, properties that I would attribute to randomness or chaos? Okay, it's not chaos. You're quite correct. The chaos in the SYK model arises from in the large N limit. However, I must also say that even without any source terms, the SYK2 model is not chaotic. It's an integrable model. Okay, so I'm not expecting to find chaos here at all. If I find chaos, then I need to think very hard about where it's coming from, because it's definitely not coming from the SYK2 model. Okay?
Okay, cool, thanks.
All right. So I'll show you where these properties are coming from right now. Okay, so we have this exact expression for the annealed spectral form factor. And I should say that in the limit that we're going to be considering, the difference between the annealed SFF and the quenched SFF becomes meaningless as well. So this is one of the reasons we're going to take the following limit. And again, this is going to be a non-physical limit. So the limit we're going to take is to set beta equal to 0. Since beta is 1 over temperature, this is the infinite temperature limit. Okay, so here G is just a function of T. I've said beta equal to 0. And in the infinite temperature limit, this is simply 1 plus e to the minus t squared over 4 cos alpha 2 times t. Okay. So now we make the following observation. One is that G at t going to 0 is 1. And you can see quite clearly if I send t equal to 0, the Gaussian factor kills off anything coming from the, well, cos is 1, so the Gaussian factor is when t is 0 is 1, so 1 plus 1 is 2, divided by 2 is 1. And as t goes to infinity, this is a half. On the other hand, when we turn off the coupling, when we turn off the source term, g of t is a half of 1 plus e to the minus t squared over 4. And this has the feature that it is a monotonically decreasing function from 1 to 2. So there's no dip, no ramp, no plateau behavior. It just monotonically decreases from g equals 1 to g equals a half. Finally, if we fix alpha, the spectral form factor, g of t, has turning points when alpha 2 equals cot of alpha 2 times t. So basically you compute g prime, you set it equal to 0, you solve this and you find this transcendental equation where when the straight line alpha 2 intersects cot of alpha 2 times t, remember t is an increasing number, you find that you get turning points. Okay, so what does this look like? Well, here's a plot then of this g of t for various values of alpha 2. And here's, sorry. here's alpha 2 approximately 0. So it's 0.001. And you can see this behavior. It's monotonically decreasing from 1 to a half. On the other hand, as we turn up alpha 2, you can see that there's a dip. This behavior here is what we will call the dip. You can see a ramp. It doesn't look very clear here, but these are actually linear. And you can see that this plateaus out to a half. Okay, so this we get from plotting the exact spectral form function, spectral form factor. Now, the key in this story is that having this exact expression for the spectral form factor, we can now see exactly where any of the oscillating stuff comes from. It comes from this cosine of alpha 2. It comes from the cosine of alpha 2 times t factor in the spectral form factor, which critically depends on turning on the source term. So without the source term, there's no behavior that's even resembling dip ramp plateau. It's essentially from t of about 5 onwards, it's just a horizontal line. From about t equals 5 onwards, in this picture, it's roughly a horizontal line. And if we computed another variant of the spectral form factor called the connected unfolded spectral form factor, we would see that apart from any transient stuff at the beginning, this was more or less exactly what we would expect for an integrable system. So this is an interesting curiosity. Even for this very simple n equals 2 fermion system, I'm starting to see behavior that resembles what I would expect for a chaotic system, namely the dip, ramp, and plateau type behavior. So then what we did was we considered the n greater than 2 fermion case. And the problem there is that for n greater than 2 fermions, the situation is analytically intractable. So you have to resort to numerics as long as the source term involves more than 2 fermions. So for the 2-point source terms, once you know the eigenvalues of the Hermitian matrix, whose upper triangular part is what I wrote down earlier, I times ji1i2 plus alpha 2 epsilon i1i2. Once you know this, you can compute you can evaluate the spectral form factor. All right, so these are what you're seeing here are plots of the spectral form factor with a 2-point source term turned on for various values of alpha 2 and n up to n equals 28 fermions. So for Jean-Gabriel, this would be n equals 14 spins. Okay, so the Hilbert space for Majorana's, you just double the value for the able to using the supercomputer at Yukawa, we were able to run these numerics for up to n equals 28. And at the bottom here, we have the same spectral form factor computed for various values of alpha 4. So now we add a 4-point source term. And again, these are for n going from 14, 16, 18, 20, 22, 24, 26, 28. And what you see is what you would expect, which is that you get this massive fluctuations in the spectral form factor, these kind of things here. And this is really a consequence of the fact that to see anything more definitive, you have to average over a large number of realizations. So I should say that in all of these calculations, we computed the spectral form factor for up to 1,000 realizations of the system. Here's some more numerics. This is now the level spacing distribution for the SYK model. SYK up here, this is SYK, sorry, SYK2 with 2-point interactions, and this is SYK with 4-point interactions. And I'm just gonna, I'm gonna skip through most of this because I realize that I've now gone 1.5 hours into the talk. So I'm just going to tell you what we found. So let me conclude by just summarizing what we found. So one, in fact, let me not write down anything. It's going to take more time. So what we found was the following. The 2 Mariano fermion case n equals 2. We have an exact solution to the 2-point source term. And the spectral form factor gives a similar behavior to what we see at higher n when we have to do things numerically. But the nice thing is that this exact solution gives us a nice intuitive feel for a probe of this dip ramp plateau type behavior that's exhibited by the spectral form factor. We can also calculate the generalized level spacing distribution function and the mean value of the gap ratio. So again, for Jean-Gabriel, the R values for this SYK2 model. And what we observe is that at late times with the source turned down, what we get is Gaussian unitary ensemble-like behavior, but in a perturbative region between the integrable SYK2 model and the integrable 4 Fermi interaction model that's not random. And then what we went on to do was to study the level statistics for this SYK model for both what are called the bare spectrum and the unfolded spectrum. And the unfolded spectrum gives a self-consistent result that we expect, but that was usually hidden in the bare spectrum. So that's what we have. And that's all I wanted to say. So yeah, thank you. Any questions?
Yeah, I've got a question. So given that the originally you sort of said there was this conjecture that the spectral form factor captures, well, so it sort of tells you how close to random matrix theory you are, is that right? Well, if you have a characteristic dip ramp.
Yes.
But are you now saying that that doesn't actually tell you if there's genuine chaos or not? Because you
Correct. I'm saying the dip ramp, that's what we're saying. The dip ramp plateau behavior doesn't tell you whether there's genuine chaos or not. All it tells you is that you have random matrix theory behavior setting in, but random matrix theory behavior itself is not enough to tell you that you have a quantum chaotic system.
Okay.
It's features, it's very specific features of the spectral form factor that you should be looking for in order to tell whether it's chaotic or not.
Okay.
Yeah. Anything else?
I wanted to ask quickly, just the that last slide that you showed with the 3 images of the spectral form factor
Yeah.
for different values of alpha 4
Yeah.
for the coupling. It looked like the dip ramp plateau behavior was more pronounced as alpha got smaller. So went from 0.1, 0.01, 0.001. At least to me it did, or is that incorrect?
Sorry, I'm trying to find this picture again. Last one, you say?
Yeah, slide 19, I think.
Okay.
You had the 3 images, and then below that was the, I think, the R statistic at the bottom.
So let me have a look.
Yeah.
Okay, this one?
Yeah. So I mean, to me, the upper figure, the bottom graph looks, well, to me, looks more reminiscent of what sort of, you know, I've been seeing from the spectral form factor in terms of having your sort of dip ramp plateau, and there the alpha 4 is, you know, 10 to the minus. Well, it's smaller than the other ones. I'm just curious about that.
That is a good point and strange.
It just looks more similar to what we saw with the small world networks rather than the upper figures.
I get that.
Yeah.
Yeah, let me think about that. That seems a little strange.
I mean, the upper ones do have a more, I mean, you have that sort of a straight line, and they do have quite a clean ramp past that small oscillation period.
Yeah.
It's just the third one resembled our
No,
small world ones.
the dip ramp,
yeah.
plateau type behavior. I think the point here is that this you can't really, this shouldn't be considered actual ramp behavior, whereas you know, this is
Right. Yeah. Okay. Okay. I see.
And there's a clean linear ramp here.
Yeah.
Averaged over the same number of realizations.
Okay.
But yeah. Okay.
Hmm.
Anything else? Okay. All right. Okay. So if that's it, let's stop here, and we will have the next seminar in the series next week, right?
That's right.
Okay. Good. Thanks, guys.
Cool.
Thanks, bro.
Thanks.
Thank you.
Happy weekends, everyone.
Everybody.
Same.
Too.
Bye.
Bye.